Today, I am going to walk you through a simulation of uniform PCM quantization, one of the foundational process in digital signal processing. Whenever we convert an analog signal like sound or a sensor reading into a digital format, we have to quantize it. That means representing a continuous range of values using a finite set of discrete labels. This simulation builds that process from first principles in Python, tests is across several bit depth and measures how quantization quality improved as we add more bits. So let's have a look. At the core of this code, the function, here you can see the function uniform PCM quantizer. It takes two inputs, x, that is the signal x, and the n, the number of bits per sample. First, we calculate L, the number of quantization levels, which is simply 2 raised to the power of n. Here you can see 2 raised to the power n. For example, with 3 bits, we get 8 levels. Since our signal is normalized between -1 and 1, positive 1, we divided that full range by L to get delta, the tape size or the width of each quantization interval. Next, we figure out which intervals each samples falls into. We shift the signal so it started 0. So shift signal to start at 0 divided by step size and take the flow. This gives us as index for each sample. We clip, here you can see, we clip the indicates so they never exceed the value range, which handles the edge case where a sample land exactly on the maximum value. We include two validation check here. Here you can see the validation check 1 and the validation check 2. So we convert every index into a binary PCM. Binary PCM what using Python string formatting. This is literally the bystream you would transmit or store. Finally, we construct the quantization signal by mapping each index back to the midpoint of its interval. That midpoint reconstruction minimize the average reconstruction error. So to evaluate how good the quantization is, we calculate two things: the mean square error or MSE between the original and quantized signal, and the signal to quantization noise ratio or SQNR expressed in discrete. SQNR tells us how strong the original signal is relative to the noise introduced by quantization. Higher SQNR means better fidelity. Here you can see the MSE mean square error and the SQNR. So for our test signal, we use simple 2 Hz. We simple 2 Hz. Here you can see 2 Hz sine wave sample at 1 kilohertz for 1 second. This gives us a clean, well understood signal, so we can clearly see the effect of quantization without other complication. So let's run the code. So after run the code, you can see the output. We run this quantizer. You can see we run this quantizer across 5 different bit depth: 2, 3, 4, 6 and 8. For each one, we record the measure SQNR from our simulation, and we also compute the theoretical SQNR using the well-known formula 6.02 times N plus 1.76 decibels. That is, you can see here the SQNR. This formula comes from the theory of uniform quantization noise, and it predicts that every additional bit should improve SQNR by roughly 6 decibels. Comparing our measured result to this formula is a great way to validate that our implementation is behaving correctly. Here you can see the first plot shows original versus quantized waveform. This version using just 3 bits, only 8 levels. You can clearly see the staircase effect. The quantized signal can only jump between a small number of fixed amplitude values. Here you can see the small number of values. So it is visibly deviates from the smooth original curve. This is the raw, audible or visible distortion that quantization introduced at low bit depth. And this is the second plot shows quantizer transfer function. Essentially input amplitude, here input quantized amplitude. Here you can see input amplitude, and this is the quantized amplitude. Instead of smooth diagonal line, which is what you have get with infinite resolution, we see a staircase pattern. Each step represent one quantization level. Here you can see the each steps is the quantization level. This is the defining visual signature of any quantizer. Now the error histogram. Here we are looking at the histogram of quantization error at 4 bits. Notice that the errors are spread fairly evenly across a narrow range. This is the classic assumption in quantization theory, that quantization noise behave approximately like uniform random noise bounded by plus or minus half the step size. And the last, this is the final part, is really the payoff of the whole experiment. It shows measured SQNR against the theoretical prediction. As we increase the number of bits, we can see the two lines track each other closely, confirming that our implementation matches theory. And you can see that unmistakable trend. Every extra bit roughly adds 6 decibel of SQNR. Going from 2 bits to 8 bits dramatically improves signal quality. This is exactly why higher bit depth audio and the higher resolution ADC give us cleaner, more faithful digital representation of analog signal. So this is the end. Finally, so we built a uniform PCM quantizer from scratch and validate it against quantization theory, and visualized for key aspect of the process: the waveform distortion, the staircase transfer function, and the error distribution, and the relationship between bit depth and signal quality. This is the same fundamental process at work every time analog signal are digitized from audio CDs to medical imaging to telecommunication. So that's all. Thank you everyone.